All right, so we're going to talk about isomorphism. And to some extent, this chapter is supposed to be self-study. There are many examples to lead you through the concepts. So I'm just going to go briefly through the chapter, and you will learn about isomorphisms by doing the exercises. All right, so one example that we have here is one that we've seen before, complex numbers. You can write a complex number as a plus bi, but really the real part and the imaginary part function to some extent independently. When you're doing addition, when doing multiplication, it's different, but we're focusing now on addition. We're focusing on the additive group of complex numbers. Now notice when you add two complex numbers, you add in the usual way. You add the first components and you add the second components. And if you think about this mapping from complex numbers to pairs, we can accomplish this mapping in two different ways. We can add the two complex numbers and get the result, or we can take each complex number separately to a pair and then add the pairs that we result with. That's illustrated in this diagram. Here's the complex numbers world. Here's the real pairs world. Okay. And here we illustrate adding two complex numbers and then translating that into a pair. Here we illustrate translating each individual complex number and then adding the pairs separately. Now there is a mistake here. Of course, when you add complex numbers, you should add the real parts, and you should add the imaginary parts. Okay. All right, so this is a translation. We've made this analogy before. It's like expressing the same thing in two different languages. Okay. Now we could run this diagram backwards also. In fact, you could change the arrows backwards here. That's F inverse, and F inverse here. So you could do the same thing. You could have two pairs and add the pairs and then translate back to complex number, or you could translate the pairs individually to complex numbers and then add the complex numbers. So there's an equivalence between the two sides. And here, this basic idea, you run through various examples of how this does or does not work in various situations. Okay, for instance, here you show that a mapping is not an isomorphism because this kind of operation diagram doesn't work in this case. So that's what the rest of the chapter is working through exercises, seeing how this general definition works in various cases. Another way of thinking about isomorphism is this idea of identification of Cayley table. Here we have a Cayley table for Z4, and here we have a Cayley table for the group generated by I, the multiplicative group generated by I. And the idea is that these two Cayley tables are the same in the sense that if I identify 0 with 1 and identify 1 with I, identify 2 with -1 and 3 with -I, and if I do this identification consistently, if every time I see a 3 here I replace it with -I, well, that identification does in fact work. They're the same Cayley table with different labelings. All right, so that's how we identify Cayley tables. Now, sometimes you may find out that this doesn't work. In that case, you do not have an isomorphism. Okay, so that's the other way of thinking about isomorphism, and several examples here about how you can make that work. So, for instance, if you wanted to show whether this was an isomorphism or not, you can do the two Cayley tables and see whether or not the labelings match up. Okay. So we have this informal definition of isomorphism. Here's a more formal definition. Two groups are isomorphic. So isomorphism is a mapping between groups. Two groups are said to be isomorphic. Notice that the group operation for G is the small dot. Group operation for H is the big dot. So two groups are isomorphic if there exists a bijection, so one-to-one onto mapping between the groups, such that the group operation is preserved. And that's this idea that if you take the group operation first and then take the mapping, that's the same thing as mapping each individual component and then taking the second group operation. Various facts about isomorphism will bring into play some of the concepts that we've seen. Isomorphism is an equivalence relation. Okay, so remember that two groups are isomorphic. So a group is isomorphic to itself. That's the reflexive property. If one group is isomorphic to another, then the second group is isomorphic to the first. That's symmetric. If group G is isomorphic to H and H is isomorphic to K, then G is isomorphic to K. So this is a standard exercise that you've done similar things before. What you're going to have to do is show, you'll have to exhibit isomorphisms that prove the isomorphic relationship. Okay. Another important property of isomorphism is that any isomorphism always takes the identity of the first group to the identity of the second group. And then you're supposed to do this self-discovery proof of that. You can also say isomorphism commutes with inverse, that the isomorphism applied to the inverse of a group element is the inverse of the isomorphized group element. So this is kind of like this whole thing about the operation, that you can apply the mapping after the operation or before the operation. Same thing with inverse. You can take the inverse and then apply the operation. That's the same thing as taking the operation first and then applying the inverse. Okay. 14.3 gives more examples. Again, this is really a self-discovery section. The approach to isomorphisms is self-discovery. One of the interesting things is that here you have isomorphism between an additive group and a multiplicative group. And it's very interesting that you can take addition and multiplication, which seem to be very different operations, and actually make a relationship between them. And that's actually what exponential and logarithm is all about. The fact that logarithms work is in fact a reflection of the fact that logarithm gives you an isomorphism between a multiplicative group and an additive group. All right, so you can discover what that means by doing these exercises. Here's an interesting thing, that we actually have a group Z which is isomorphic to a subgroup of itself. That's one of the interesting things about infinity, that you can make one-to-one onto mappings between a set and its subset if the set is infinite. Here's another example of two groups of integers, additive groups of integers. These turn out not to be isomorphic. Here's two multiplicative groups of units. It turns out that these are isomorphic. Quite interesting that although the origins are somewhat different, the two groups are in fact isomorphic. They have the same structure and the same relationships between group elements. So some more isomorphisms between different types of mathematical objects. And you see that isomorphism kind of tends to unify mathematics by bringing together apparently different groups and showing that they're really the same group. Okay, so I think I'm going to stop here. Well, let me see, what do we have here? All right, some other properties of isomorphism that kind of make sense, that if one group is abelian, it can only be isomorphic to other abelian groups. So an abelian group is never isomorphic to a non-abelian group, and you can work through that proposition. And that kind of makes sense. If you're preserving the operation, how could one group preserve the operation and one be commutative and one not commutative? Okay. Same thing with a cyclic. You prove that a cyclic group can only be isomorphic to another cyclic group. Okay, so you could say isomorphism preserves cyclicity, something like that. Okay, let me stop here and we'll go on with the next video.